तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, up to now in this course we have gone through all the gone through some of the BJT models, and as well as we have studied in detail the BJT inverter circuit, and now we are in a position to start on the different bipolar logic families, okay, and see how this inverter circuit together with some other additional circuitry give rise to the different logic families, okay. So, we shall in fact take up the TTL gate first, okay, and see how it actually evolved, okay. Now, for that first let us look at this circuit, okay. It consists of resistance, power supply of course, and two diodes. So, if we call this input A, input B, the two inputs, and the output Y, okay, and I say that this is a logic circuit, that is the output Y is a Boolean function of the logic inputs A and B. Now, what is the logic which you derive from this circuit, okay? That is, suppose, that is, you have to look at it this way, that is, suppose if both the inputs are low, okay, what is the nature of the, what is the state of the output? It is going to be low, okay. Suppose one input is low and one input is high, what is the output? It is still going to be low, because if this is low, say there is a conduction here, okay, one of the diode whose in suppose if A is low, this particular diode is going to conduct, the current is going to flow, okay, and this point is also going to be low. Now, suppose if both the inputs are high, okay, all right, then what is the state of the output? The output is also going to be high, okay, because this input is high, that means there is going to be very little conduction here, okay, all right. Suppose this is VCC is 5 volts, if you also apply 5 volts here, okay, these diodes cannot conduct, okay, and the output, there is no current flowing here. So, this output is also going to be 5 volts, all right. Now, so this behaves as a, what gate is it? It is going to be a, it is going to be an AND gate, okay, because only when both the inputs are high, the output is high, okay. When A and B is high, then only the output is high. For all other cases, the output is low, all right. Now, you know that AND gate, with an AND gate you cannot realize all logic functions. So, usually in logic family, the basic or the standard or basic gate of a logic family is usually one of what are called the universal logic gates, okay. The universal logic gate is a gate with which you can realize any Boolean function, okay. And what are these universal logic gates? Yeah, they are either the NAND gate or the NOR gate. So, usually you have this basic gate is either a NAND gate or a NOR gate. Now, how do you convert this AND gate to a NAND gate? You have to follow it up with a inverter, okay, and we are aware of what is an inverter circuit, okay. So, we will add an inverter here, a well known inverter circuit, and take the output here, all right. So, this should give us a NAND gate, because we had an AND function here and we have a NAND here. We have an inverter here. So, this should give us a NAND gate. but does it really work? That is what now we have to see, whether this circuit is really going to be functional. Okay. Now, so now the question is, when this input is low, when any of the input is low, the output should be high, okay, because this is a NAND gate. All right, which means that when any input is low, this transistor, the output transistor, should be cut off. All right. So we have to ensure that when any input is low, the output is cut off. All right. Now suppose the input low, usually for a logic gate, BJT, we usually take it as 0.2 volts, because that is the voltage of a saturated transistor, the collector emitter voltage of a saturated transistor. Okay. So suppose we have a 0.2 volt here. Okay. This can be anything. Okay. 0.2 or 5 volt, doesn't matter really. Okay. Now if this is 0.2 volts and there is a current flowing, current will flow through this, okay, this path, okay, and what is going, so there is going to be a drop across this diode when this diode conducts. Okay. Suppose we assume that this diode has a drop of 0.7 volts when it is conducting. So what is the voltage at this point here? 0.9 volts. So this voltage is 0.9 volts. Now if you have a 0.9 volt here, okay, we have seen the BJT inverter characteristics. If this is a 0.9 volt here, what happens to this transistor? This transistor is going to be in saturation. But what we actually want is that this transistor should be cut off. All right. When any input is low, this transistor is cut off. So although it looks nice and followed by an inverter NAND, but it is actually not going to work. So how do you modify this circuit in order that it is going to work? Okay. Small modification is needed. Okay. Yeah. Suppose it's correct. Suppose we replace this resistance here with a diode. Okay. Now I am going to replace this resistance with a diode. Here I remove this resistance and I put a diode here. Okay. All right. Now this voltage is 0.9 volts here. Okay. Now what happens is, this 0.9 volts is going to be dropped across this diode as well as this base emitter junction. Okay, and considering that the base emitter junction is also a PN junction, these diodes are quite similar. Okay, base emitter junction diode you can say, as well as this external diode. Okay, let us say that this 0.9 volt is going to drop shared equally between these two. Okay, so the drop is going to be 0.45 volts across each, and let us say if for this diode to conduct, okay, you require at least 0.6 volts. Okay, there is going to be no conduction. Okay, there is going to be no base current. This transistor is going to be cut off. Okay, all right. So this circuit will work as an inverter, as a NAND gate. Sorry. Okay, because when this input is lower 0.2 volts, then here is 0.9 volts. This transistor is off. Okay. Now when you raise this input, okay, what actually happens is, when you raise this input, this voltage also is going to get raised. Okay, and suppose when this voltage goes to 1.2 volts, say, okay, then you have 0.6 volts across this, each of them. Okay, and when it goes even above that, then it starts conducting. The transistor turns on. Okay, the output voltage is going to fall. Okay, so when the input goes high, basically, all right. Okay, what is going to happen if this input is sufficiently high? Say even if this input goes to 5 volts, okay, you have a current flowing here. Okay, this transistor is going to turn on. Okay, output is going to be low. All right, so this circuit actually behaves like a NAND gate. Okay, all right. Although one must say that this characteristics is not good, but we will not go into the details of this. All right, but okay. But this circuit again has a very serious problem. Okay, problem with this circuit is related to its switching properties. Okay. I am just giving a hint, it is related with its switching properties. Okay. That is, we have seen the switching of a bipolar transistor. Okay. Now, if you want to switch off a bipolar transistor, what do you require? When the transistor is to be switched off, okay, you have to remove, say when this transistor goes from saturation to cutoff, you have to remove the excess stored charge in the base. Okay. Now, how do you remove this? This base charge has to be removed by a reverse base current. All right. Now, this removal of this reverse base current is very important in switching switching of a bipolar transistor, otherwise it will take a long time. Okay. So, you require a reverse base current. So, so is there a mechanism for providing a reverse base current? There is no mechanism for providing a reverse base current. Okay. So, it will take a long time to switch off. Okay. Now, what can be done is some modifications to provide a resistance like this. Okay. So, there is a negative supply voltage is provided. Okay. You have a base resistance like this. All right. So, normally what is going to happen, a current flows in, turns it on, but when this when this input goes low, this voltage is low, then this is say around 0.7 volts. Okay, this is a negative voltage. A reverse current flows this way. Okay, to switch it, to switch off the transistor. Okay, but this is not a good solution from 2 points of view. One is that you require a negative power supply, which is not a good thing, because you have to have a dual power supply, which is not convenient for any circuit engineer. Okay. Number 2, if you put a resistance like this, when the transistor is switching on, okay, the current has to flow into the base. Okay, and a part of that current actually gets diverted here. Okay. So, the entire current does not flow into the base, and so it slows the device. Okay. You know that in order to switch on the transistor, you require a sufficiently large, we have already seen that, okay, on time of a transistor, that is, you require a sufficient large base current flowing into the base of the transistor, but this is going to divert some current. All right. So, this is not a good solution. All right. So, but in fact, this is one of the earliest logic families, okay, basic circuit of the earliest logic families, called the diode transistor logic. Okay. This circuit DTL, okay, diode transistor logic. But this has the drawbacks which I just mentioned. Okay. It is a very slow circuit because of these problems associated with switching. Okay. All right. Now, the TTL, or the transistor logic, is actually derived from this circuit. Okay. Now, if you look at this structure here, okay, this structure here, okay, the two diodes here, okay, and this diode here. Okay. Now, this particular structure can be replaced by what is called a multi-emitter transistor. I will just come to that. What is a multi-emitter transistor? Okay. This is nothing but, again, similar to this, you have two p-n junctions this way and one p-n junction this way. So, this is two p-n junctions, okay, but it is a transistor structure basically. All right. This is called a multi-emitter transistor, and then if you have the same thing, so it is actually the same circuit. All right. We have replaced these 3 diodes, okay, with a multi-emitter transistor. Okay. All right. Now, so these are the inputs here, and this is the output point. Okay, exactly the same circuit. Now, what is a multi-emitter transistor? I will just tell you. A multi-emitter transistor is, I just come here. Okay, I will draw the figure of a multi-emitter transistor. You are familiar with this. a normal transistor structure now, by now I suppose. So, this is the base, then you normally have one emitter. Suppose you have two emitters like this. Okay. So, this is say emitter 1 contact, you have a second emitter contact here. I am sorry, I have to take the base contact. All right. I take the base contact here from this region. This is the collector. Okay, so this is NPN, NPN. This is N plus. Okay, of course, you have the buried layer here also, which is so this is P. So this is the BJT structure of a this is the structure, cross-sectional structure of a multi-emitter transistor. You see, the difference between a normal transistor and the multi-emitter transistor is that instead of having one emitter, you have two emitters. So basically, it is like, this is one transistor, this is another transistor. So there are two transistors, okay, with a common collector base junction. So this is the collector base junction. Okay, this is common to both the transistors, and you have two emitters in the base. So if you look at the cross section, if you look at the top view, okay, I'll just draw the top view also for you. Okay, this is the base. Okay, this is the collector diffusion N plus. And you have the collector contact here, you have the base contact here, and then you have two emitters. Okay, and these are the two emitter contacts. Okay, so this is E1, emitter 1, this is emitter 2, this is the base, this is the collector. This is the top view looking from the top. Okay, and this is the isolation region. Okay, on which the transistor is placed. Okay, so this is the multi-emitter transistor. Basically, again, just to repeat, a multi-emitter transistor is a transistor with a common collector base junction, but separate emitter base junction. So you can consider them as transistors in parallel as such. Okay, there is a space saving if you have a multi-emitter structure rather than having to fabricate two separate bipolar transistors. Okay, all right. So we go back to the circuit here with a multi-emitter transistor and see how this transistor actually behaves as a NAND gate. How this circuit behaves as a NAND gate. Again, we have the two inputs A and B. This is the output Y, say. So this is one resistance, this is the other resistance. Okay. Now what happens is, suppose this input here goes low. Okay. What happens? Say this is 0.2 volts. Okay. Suppose this is 0.2 volts here. What is this voltage going to be? Around 0.9 volts, say. Okay, and suppose this resistance is 4 kilo ohm, okay, and this is 5 volts. Okay, so a current 5 volts minus 0.9 volts divided by 4 kilo ohm, around 1 milliampere current flows here. That is the base current. Okay, and this flows into the emitter. Okay, okay, this transistor is behaving as a normal, working in the normal mode now, and there is a tendency of a collector current to flow in this direction. All right. Okay, but of course a current normally cannot flow out of the base, so this behaves as a very high resistance, you can say. All right, and this transistor with almost a zero collector current is what is in this, which state it is in saturation, you can say. Very high base current, very small collector current. Okay, all right, but there is no current. So this transistor actually gets no base current. Okay, so what is the state of this transistor? It is off. Okay, it is cut off. So the output is going to be high. All right, when any input goes low, the output is high. When both the input goes high, when you raise the input, okay, what is going to happen is, you see, this is a PN junction here. All right, there is another PN junction. This is PN. This is another PN. All right. Okay, this is NPN. All right. Now, this, that a PN junction, okay, cannot be forward biased by more than, say, it cannot be more than 0.75 or maximum 0.8 volts or so. Okay, it cannot go beyond that because of the nature of the characteristics of a PN junction. Okay, if the forward voltage goes higher than that, that means a very large current is flowing, and which cannot flow because of this limiting resistance. Okay, so the voltage across this PN junction, okay, let us assume will be around 0.7 volts or so. Okay, so this voltage here at this point, okay, cannot be more than, that is the base of this multi-emitter transistor, this voltage cannot be more than 1.4 volts or so. Okay, because if it is more than 1.4 volts, it would mean that one of these PN junctions is forward biased by more than 0.7 volts or so, which is not possible. Okay, so if this voltage is 1.4 volts or so, and suppose you have raised this voltage to much higher than that, okay, that is this emitter input point, what does it mean? This junction is, emitter based junction is reverse biased. The emitter based junction is reverse biased. And what is the state of the base collector junction? Forward biased. So for this transistor, it's a peculiar situation. The emitter based junction is reverse biased, whereas the base collector junction is forward biased. Okay, you normally operate the transistor in the other way, that is the base emitter junction is forward biased, base collector reverse biased. So it is called the reverse active mode of operation. Okay, it is working in the reverse mode of operation. And when it works, when a transistor works in the reverse mode, okay, that is basically you have interchanged the emitter and collector terminals. Okay, what is the nature, what is the value of beta? The beta of the transistor is very small. Okay, now again, you see what is happening is this voltage is around 1.4 volts now, say. Okay, if this voltage is 1.4 volts, this is 5 volts supply, so a current will flow into the base. All right. Okay, there is a base current for this transistor. Okay, now the beta of this transistor is very low. What does it mean? In fact, these transistors are so designed that the beta reverse, okay, the reverse beta of this transistor is approximately made very small, about say 0.02 or so. Okay, so it means that the collector current by the base current ratio of this transistor is going to be 0.02. All right. So a very small current. So this is now behaving as the collector. This is behaving as the emitter. If you look at it as the normal operation. So this current is very small, and it is in the reverse mode. So this is behaving as the emitter. So if the collector current is very small, and you know that the emitter current is the sum of the base current and the collector current. Okay, so you can say that the emitter current is almost equal to the base current. So whatever is the current flowing here is this almost the same current flows in like this. Okay, and this current is quite large. That is almost it is 3.6 by 4K. That is around 0.9 milliamperes. Okay, and so this about 0.9 milliamperes the base current flows into this transistor, and that should be large enough to make this transistor go to saturation. All right. So when this input is high, okay, this current flows into the base. Basically what is happening is, if you look at it, this voltage here cannot rise above a certain value. So there will always be a current flowing here into the base of this transistor. When this input is low, that current flows into the input. okay, and no current flows into the base. So, this transistor is starved of current, so it is cut off. When this input goes high, this current which is flowing into the base of this multi-emitter transistor flows towards the input of this transistor, okay, and this transistor turns on and goes to saturation. All right. Okay. So, this transistor goes to saturation, the output voltage goes low. So, we can say that when both the inputs are high, okay, this transistor, the output transistor goes to saturation and the output is low. Okay. So, this behaves as a NAND gate. Okay. Now, suppose this transistor is in saturation and suddenly you make this input go low. Okay. What is going to happen? This transistor, okay, this input has gone low. So, this transistor will go back into the normal mode of operation from the reverse mode. Okay. This becomes say 0.2 volts here. Okay. This voltage goes to 0.9 volts. The current flows into the it is in a normal mode. This junction gets forward biased. The emitter base junction gets forward biased. So, there is a base current flowing in, and so there will be a tendency of a collector current flowing, okay, and this collector current, okay, what is it doing? It is removing the stored charge, base stored charge of this transistor. Okay. Suppose we have seen if this is 0.2 volts and this is 0.9 volts here, the base current is 1 milliampere, slightly more than 1 milliampere. Okay. And if the beta of this transistor is say even to conservatively say 25, okay, the collector current should be around 25 milliampere. It can support a collector current of 25 milliampere. Okay. So, a large current will flow out of the base of this transistor because there is charge stored. This can support the collector current till the point that there is charge here. Okay. So, this is drawing out the base charge of this transistor, okay, and this current is going to exist as long as the base charge is there. Okay. Once this charge has been removed, okay, there is no voltage source here, no, there is no source of charge. So, basically this collector current is going to go to 0, this transistor goes to saturation. Okay. So, you see the when you compared with the DTL circuit, okay, this is a similar situation. As I said, this circuit looks similar. Basically, you have converted 3 diodes into a multi-emitter transistor, but the advantage is the transistor action here, okay, and this transistor, okay, by its transistor action actually provides a very large current, okay, to remove the base charge of the output transistor when that transistor is to go from saturation to cutoff. All right. So, that is the major advantage of this circuit. Okay. So, this is the basic TTL circuit, okay, transistor logic circuit, and in fact the propagation delay of this circuit when you compare to the previous circuit here, the diode transistor logic circuit, okay, is about 1/10. Okay, the propagation delay is about 1/10. So, you have an order of magnitude improvement in speed, okay, from the TTL from the DTL because of the improved removal of base charge storage mechanism in the TTL circuit. Okay. So, this is the TTL basic transistor logic circuit. All right. Well, so we know that this circuit now behaves as a NAND gate and is much better than the previous DTL circuit. But again, this circuit has its share of problems, okay, or I mean everything has its problems, but we have to look at ways how to improve it. Okay. So, the delay, most of the delay associated with this circuit is, that is, suppose this circuit is driving a capacitive load. Okay. Now, when this transistor goes from saturation to cutoff, okay, what is going to happen to the output voltage? the output voltage should rise from say low to high. Okay, so this point the voltage should rise from low to high. Okay, now if you have a, this is cut off. So how can this point, so this capacitance, you know, when it was low, the voltage across this capacitance was low. Okay, now when this point has to rise, this capacitance has to get charged. So a current must flow. Normally when this is saturation, the current flows into the transistor, but when this goes off, transistor has gone off, the current flows into the capacitance, charging the capacitance. Okay, and the delay of this process is given by the RC time constant, correct. Now, so in order to reduce the RC time constant, of course you cannot reduce C because that is the load. Okay, you have to, for a particular load, if you want to reduce the RC time constant, you have to reduce the collector resistance. But collector resistance, if you reduce, there is some problem. The problem is that when this transistor is on, that is the output transistor is on, if this collector resistance is low, you have a large current flowing, okay, and the power dissipation is going to be more. Also, if the collector resistance is low, it is difficult to drive this transistor to saturation, isn't it? Because IC sat, okay, that is going to be much higher, okay, and you require a larger base current to actually drive the transistor to saturation. So the on time in fact is going to go up. Okay, so there are so RC you cannot make it too low. Okay, now basically our requirement is, okay, that when this transistor, output transistor is off, okay, I shall write it down here. When I should let me call this TO, let us say output transistor. Okay, when TO is off, okay, we want RC to be low. Okay, because of the low RC time constant. And when T naught is on, we want RC to be high. Okay, so basically we have two conflicting requirements. Okay, and you cannot achieve that same these two requirements with a passive resistance. Okay, with any passive element, because the resistance will always have its same values. No, it cannot change its value. It is always going to have the same value. So what you require is an active element. Okay, that is a transistor, for example. Okay, a transistor in its off state will behave as a very high impedance. Okay, and in on state will behave as a low impedance device. Okay, so we require a circuit with what is called an active pull up. Okay, this resistance is called pull up resistance because the output is actually pulled up through that resistance. So this is the pull up device and this is the pull down device, because when you want to, when the output has to be pulled down to low values, this capacitance has to be discharged through this. Okay, this turns on, the capacitance discharges through this. So this is the pull down device, that is a pull up device. So what you require is, instead of a passive pull up, you require a active pull up. All right, you understood why we require that. So now we shall again modify this circuit and goes to the next stage of development. Okay, so it has developed with time in this fashion. So okay. The next circuit. So this is VCC 5 volts, TTL power supply voltage is 5 volts. Okay, so this is this is the very familiar well-known circuit for the 7400. okay, that is the chip number 7400 NAND gate. Okay, all right. So this is 4 kilo ohm, this is 1.4 kilo ohm, this is 1 kilo ohm, this is 100 ohms. Okay, so this is the well-known circuit, okay, which you see that the resistance has been actually replaced. So this is the output side. Okay, this is the same input side as previously. This is the output side, and this is the output transistor, the pull down transistor, which is still there. And in the pull up side, you have these many components now. I shall come to that, why you require all of them. Okay, so this is the pull up side you have replaced, and you have a circuitry here, consisting of one transistor and two resistances here. This is what is called the phase splitter. Okay, now the idea, what the purpose of this is, that is, this when you have a transistor, okay, and it behaves as an amplifier, the emitter point is actually has a positive gain, whereas the collector point has a negative gain. Okay, so the this transistor actually achieves the purpose of, so when one of these transistors is on, the other will be off. Okay, so when this is on, the pull down is on, the pull up will be off. When the pull down is off, the pull up will be on. So that is what is achieved by this part. Okay, which okay, so we shall again just go through this circuit qualitatively first. Okay, what is happening? Okay. Now again, just like in the previous case, these are the two inputs, say this is the output. When any input goes low, all right, this transistor is working, the multi-emitter transistor is working in the normal mode. Okay, and when it works in the normal mode, there is a tendency of a current to flow out. So what happens to this transistor? So let me give it, call this T1, this is T2, let me call this T3, and let me call this T4. Okay, so what happens to T2? T2 goes off. All right, and when T2 is off, okay, what happens to T3? T3 will also be off, because if T2 is off, there is no way the T3 can get any base current. Okay, so because the base current of T3 could only be supplied by the emitter current of T2. All right, so T2 is off, T3 is off. Okay, what about T4? It is on because its base is connected via resistance to the power supply. Okay, so it is going to get sufficient base current. Okay, base current is going to flow into into T4. Okay, and this transistor T4 turns on. Okay, and when this transistor turns on, well, this provides a low resistance. Okay, and to connection to the output. Okay, so we shall see what exact values and all. So this transistor turns on. So when T3 is off, T4 is on. Okay, all right, and the resistance seen at this output end is actually the base resistance divided by beta of this transistor. You know that how you reflect the base resistance onto the emitter side. Okay, so that is going to be a low resistance. Okay. Okay, now what happens when we look at the other situation? What happens when the input goes high, when the inputs go high rather? Okay, then what is the state of this transistor? It is acting in the inverse mode. Okay, so the current which flows here, okay, is going to flow into the base of this transistor. Okay, it flows into the base of T2. T2 turns on. Okay, there is going to be a large emitter current flowing. Okay, and of course a part of it goes here, but major portion flows into the base of T3, because the emitter current is beta times the base current. So there is a large emitter current here. Okay, so T3 will get very large, sufficiently large base current to turn it on, go to saturation in fact. Okay, all right, and what happens to T2? What happens to T4? That is what we have to see now. Okay, suppose T3 goes to saturation. Okay, then what is this voltage at the output? Low, say 0.2 volts. Okay, and what the base, the voltage at the base here. Okay, suppose we assume this to be around 0.75 volts, say. Okay, that is the base of transistor T3. All right. Now this T2 also, let us assume this has gone to saturation. All right. Now what is the voltage at the collector of T2 in that case? 0.75 plus 0.2. So it is going to be 0.95 volts. All right. So you have a drop of 0.75 volts between the base of T4 and the collector of T3. Okay. So you have a 0.75 drop shared between the base emitter of T4 and this diode here. Okay. This actually explains why we require a diode here. Okay. If the diode was not present here, okay, this transistor would never have gone off. But now this 0.75 volt is shared between these two PN junctions. So neither of the PN junctions can turn on. Okay. So this is going to be off. So basically at the collector of this transistor T3 you see a very high resistance. All right. So we have achieved, okay, what we have set out for, that is when T3 is off, okay, you see it sees a very low resistance because T4 is on, okay, and when T3 is on, okay, this goes to saturation, you have a very high resistance working here. So you have very low collector current flowing. Okay. So all right. So this is the basic TTL circuit, okay, 7400 NAND gate, okay, which was available commercially in the mid 60s, okay, one of the earliest versions of the TTL gate. Okay. So so the next thing what we should do is now we should go into it a little more quantitatively in order to understand the working of this circuit, that is the input output voltages, how it looks like, the characteristics, okay, all right, of this circuit. Okay. And all right. So I don't know, maybe we shall take it up in the next class because we don't have sufficient time for going through this class. Okay. That is what is the nature of the input output characteristics. All right. We shall study that. Okay. And then we shall look into further modifications. Well, this is the first early version of TTL. Okay. Well, the TTL gates which are available nowadays, okay, have been further modified, okay, many number of times. Okay. So we shall see again. So this has its drawbacks and the further modifications, how they improve their properties. So in fact, just to tell you that this particular gate, all right, this particular NAND gate had power dissipation, okay, of 10 milliwatts, okay, and a propagation delay of 10 nanoseconds. Okay. This power dissipation of 10 milliwatts per gate and propagation delay of 10 nanoseconds. All right. So we shall go ahead with this in the next class and see. We shall see how exactly as we go along and see further improvements, how these properties have been improved upon. Yes, you have a question.
Sir, how that phase splitter will work so that one of the T4 or T3 only turn on?
Yes, basically we have discussed that qualitatively. Quantitatively we will see in the next class. Okay. What happens is when this input, you see, when this input is changing, okay, this circuit behaves as an amplifier, okay, and this amplifier has a gain, you know, if you have a collector resistance of 1.4 k and emitter resistance of 1.1 k, this circuit has a gain of at the collector point it is a gain of minus 1.4, all right. So basically what is happening is when this input is rising, okay, this emitter voltage is going to rise, okay, but the collector voltage is going to go down, okay, all right. So when this emitter voltage rises, it turns on T3, okay, whereas it cuts off T4, okay, because of the negative gain at the collector point. Whereas, you know, the other way, when you can look at it this other way, that is when the input voltage is reducing, okay, this T3 is cut off, you know, and the T4 goes into conduction. So basically that is why we have already seen sort of that when T3 is on, T4 will be off, and when T3 is off, T4 will be on. Next class we shall see it in more quantitatively, okay. We shall put down values and see what is the exact at what input voltages exactly these transitions take place, that is one transistor going off and the other turning on and so forth, okay. That is, we are going to do it more quantitatively so that we can we can understand the exact we can actually derive the exact input output characteristics of this gate, okay, which is important because that will also help us to understand, I mean, when the further modification, what further modifications are required to improve the input output characteristics, okay. So that will give us an idea of the next generation of TTL gates, how they have developed, what modifications were done and so on, okay. So